And next topic is effects of dielectrics in capacitor. Suppose the dielectric like mica, glass or paper are introduced between the plates, then the capacitance of the capacitor is altered. Therefore, the dielectric can be inserted into the plates in two ways. First one is known as when the capacitor is disconnected from the battery. Second one when the capacitor is connected to the battery. So first one we will discuss, that is when the capacitor is disconnected from the battery. Here we can consider two parallel plates of each cross-sectional area is A, which are separated at the distance D. Then V0 is the battery voltage and the stored charge is Q0. Therefore, the capacitance C0 equal to Q0 by V0. And next, the battery is then disconnected from the capacitor and dielectric is inserted between the plates. Therefore, the introduction of dielectric between the plates will increase the electric field. Therefore, E equal to E0 by ER. E0 is nothing but it is known as the electric field when no dielectric, and ER is known as the relative permittivity. ER value is always greater than 1 and comparatively E and E0, E is lesser than E0. Therefore, E equal to E0 divided by ER. Then the electrostatic potential difference between the plates is equal V equal to ED. Therefore, the E value is E0 by ER we can substitute. Therefore, E0D divided by ER and this is equal to V0 by ER. Therefore, the capacitance is inversely proportional to potential. Therefore, potential decreases, capacitance increases. Now, the new capacitance C equal to Q0 by V, which is equal to ER Q0 by V0. But C value is ER C0. The ER value is always greater than 1 and C is also greater than C0. Therefore, C equal to ER E0 A divided by D, which is equal to EA by D, where E equal to ER E0. This is known as the permittivity of dielectric medium. Now, the energy stored in the capacitor U0 equal to half into Q0 square by C0. But after dielectric is inserted, the Q0 value is constant but C value is increased. Therefore, U is equal to half Q0 square by C, which is equal to half Q0 square divided by, instead of C we have to write it as ER C0 and half Q0 square C0 value is U0. Therefore, U0 by ER. Therefore, U equal to U0 by ER. ER value is always greater than 1 and U value is lesser than U0. Therefore, there is a decrease in energy because when the dielectric is inserted, when the capacitor spends some energy in pulling the dielectric inside. And next second topic is when the battery remains connected to the capacitor. Let us now consider the battery of voltage V0 remains connected to the capacitor when the dielectric is inserted to the capacitor. Now the potential difference V0 across the plate remains constant and the experimentally it is found, and when dielectric is inserted, the charge stored in the capacitor is increased by the factor ER. Therefore, Q is equal to ER into Q0 when Q is increased and capacitance is also increased. Therefore, C, the capacitance equal to Q by V0, that is Q value is ER Q0 divided by V0 and which is equal to ER into C0. Because C0 equal to E0 A by D, therefore C equal to EA by D. Then U0 value equal to half C0 V0 square. Therefore, U0 equal to half Q0 square by C0. Because here both the Q and C are changed, whereas the equation A, the V0 value is constant. After dielectric is inserted, the C value is increased. Therefore, U equal to half C V0 square, which is equal to half ER C0 V0 square, which is equal to ER U naught. Here ER value is greater than 1 and U value is greater than U naught. Suppose the voltage between the capacitor V naught is constant, the electric field between the plates remains constant. Therefore, the energy density U equal to half E naught square, and E is nothing but it is known as the permittivity of dielectric material. Here there is one tabular column which is easily understand the dielectric which is connected to the battery or disconnected, and dielectric is inserted, and when the battery is connected, charge Q is constant, voltage decreases, electric field decreases, and capacitance increases, and last energy decreases. When the battery is connected to the dielectric, therefore the charge increases, voltage constant, electric field constant, capacitance increase, and energy is decreased. Now in this video we will discuss about the capacitors connected in series. Take three capacitors of capacitance C1, C2, C3 which are connected to the battery. In this battery, plus and minus terminals are there. From the minus terminal, charge Q transferred to the right side of the capacitor, and then this Q value is pushed to C2, C1. Therefore, the potential difference in between C1 is V1, C2 is V2, and C3 is V3. Therefore, the total potential V equal to V1 plus V2 plus V3. Since Q equal to CV, therefore V equal to Q by C. Substitute the value, therefore Q by C is equal to Q by C1 plus Q by C2 plus Q by C3. And Q is common, take it out, therefore Q into 1 by CS equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. Therefore, Q cancel on both sides. We can get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Therefore, the inverse of the equivalent capacitance Cs of three capacitors connected in series is equal to the sum of the inverse of each capacitance. This equivalent capacitance Cs is always lesser than the smallest individual capacitance in series. And next we will discuss about capacitors connected in parallel connection. Suppose if you take three capacitors which are connected parallel, and the capacitance is C1, C2, C3, and the charge is Q1, Q2, Q3 which is connected to the battery. Therefore, Q equal to Q1 plus Q2 plus Q3. Since Q equal to CV, therefore CPV equal to C1V plus C2V plus C3V, and V is constant, you take it out for both the sides. Therefore, CP into V equal to V into C1 plus C2 plus C3. Both the sides V is cancelled, so we can get CP equal to C1 plus C2 plus C3. Therefore, we can write it, the equivalent capacitance of capacitors connected in parallel is equal to the sum of the individual capacitance, and the equivalent capacitance Cp in a parallel connection is always greater than the largest individual capacitance.